I thank the organizers for providing me this opportunity to speak, and I apologize for doing so over Zoom. This is for reasons beyond my control, having to do with health. In any case, let's get started. So I will probably be duplicating a lot of what Dawn and Tony said in their earlier lectures. In any case, I'll be talking about M, which is a toric manifold, meaning that it is equipped with the effective action, Hamiltonian action of, so it's assumed to be a symplectic manifold. It will be equipped with the effective action of Hamiltonian action of a torus of half the dimension of the manifold. And I will denote the moment map by phi. So there is some comparison with integrable systems. An integrable system is a symplectic manifold equipped with n linearly independent Poisson commuting functions, which are linearly independent, meaning their Hamiltonian vector fields are linearly independent almost everywhere. So a toric manifold is an integrable system for which the functions may be chosen in such a way that the Hamiltonian flows of the Poisson commuting functions are periodic with period 1 almost everywhere. The image of the moment map is a convex polyhedron, which I'll denote by B. This is the Newton polyhedron of M. I apologize, I cannot actually see the chat, and so if there are any questions from the audience and questions in the chat, please interrupt me. Please feel free to interrupt me. So all polytopes arising from toric manifolds satisfy that for every vertex P, there are exactly n edges leaving it. And the edges are of the form P plus TV. T is just a parameter, where Vj is an element of the weight lattice. So I'll write this as the dual of z to the n. And I'm also assuming that the weights v1 up to vn form a basis of the weight lattice for every vertex. If only the first two conditions are satisfied, then M is a toric orbifold rather than a smooth manifold. I will be referring to references by Michel Audin and Victor Guillemin. Those will be given at the end. So we will see that in the situation where B is a convex polytope satisfying the three conditions I listed above, then there is a toric manifold so that the image of the moment map is this polytope B. Dalzin showed that toric manifolds are classified by their moment polytopes. In other words, if you have two toric manifolds which have moment maps phi1 and phi2, and their images are equal, then there is a Tn equivariant symplectic diffeomorphism between M1 and M2. What is shown, the first assertion is existence. If you have a polyhedron satisfying these conditions, then there is a toric manifold whose moment image is this polyhedron. And what Dalzin showed is uniqueness. If you have two such that have the same polyhedron, then they are equivalent up to equivariant diffeomorphism. So to see these conditions, given a polyhedron B satisfying these conditions, we exhibit a toric manifold that has that polyhedron as its moment map. So I'll write B as the intersection of D hyperplanes. or d half planes, like so. The lambda j are just real, well, positive real numbers. I should have written uj are vectors, the normal to the edge of the polyhedron. If B is an n-dimensional polyhedron in Rn, then when f sub I is an I-dimensional face, I will be an I simplex. The interior of f sub I, this is just congruent to the interior of the I simplex. And every point in B is in the interior of exactly one face. A facet is an n-1 dimensional face. So the number of facets in B is D. They're indexed by the J, and the normal vectors to these facets are the use of J that appeared on the previous slide. The use of J are assumed to be primitive. In other words, they are not given by an integer multiple of another element of Z to the n. We have a short exact sequence of vector spaces. So Rd, then there's a map pi that goes to Rn, and another map I that goes from, this is really the kernel of this, little script n. So here pi takes, so E sub j is just the unit vector, Euclidean unit vector in Rd. There are d of those. And U sub j are these normal vectors. Because the U sub j are in the weight lattice, this exponentiates to a sequence of abelian groups. So you have the identity going to n, which goes to U1 to the d. I'll call that map also I, and U1 to the n, and I'll call this map also pi. So n is the kernel of pi, and this is a torus. We know that the moment map for the action of U1 to the d on CD is written as J sending, so the Z's are complex numbers, so send Z1 to ZD up to at -1/2, and then norm squared of Z1 squared up to ZD squared. And then you can add a real number. No, sorry, a vector. So those become the numbers that tell you where these lattices, where these hyperplanes are. So for the action of n on CD, the moment map is I star composed with J. So here we have the dual sequence, Rn star going to pi star, going to Rd star, going to I star, going to script n star, going to 0. So here script n is the Lie algebra of n, so that's isomorphic to R to the n minus d. Sorry, this should be d minus n, that's a mistake. So we reduce CD with respect to the action of n. So I star composed with J inverse image of 0 quotiented by n, that is a symplectic manifold. We will see why. And secondly, it is equipped with the Hamiltonian action of t to the n with moment map phi, and the image phi of m is our polytope B. So here's an example, CP2. The moment polytope is the right triangle with vertices 0, 0, 0, 1, and 1, 0. I'll let u sub I be the normal vector to the ith face. So u1 is 0, minus 1, u2 is minus 1, 0, and u3 is 1, 1. But this probably should be 1 over square root of 2. So our sequence says you have script n going into R3, going into R2. So it sends, pi sends e sub I to u sub I. So sends, 1, 0, 0 goes to 0, minus 1. 0, 1, 0 goes to minus 1, 0. And 0, 0, 1 goes to 1, 1. And in this case, the lambda 1 and lambda 2 are both 0, and lambda 3 is 1/2. And the matrix is 0, minus 1, 1, and minus 1, 0, 1. That is similar to the matrix that appeared in Tony's lecture when he did this similar example. So script n is the real numbers times 1, 1, 1. This sits inside R3. Big N is isomorphic to U1. So we reduce C3 with respect to N. That tells us, so I sends 1, 1, 1 to R3. I star sends R3 to R. I star sends V to the inner product of V with this vector 1, 1, 1. So J sends Z1, Z2, Z3 to lambda 1, lambda 2, lambda 3 plus minus 1/2 and the sum of these norm squareds of Z1 squared, Z2 squared, Z3 squared. So the inverse image, well, I star of J of Z1, Z2, Z3 is the sum of the norm squareds plus lambda 1 plus lambda 2 plus lambda 3, which gives you minus 1/2 times sum of the norm squareds plus 1/2. So finally, we get that you have that the sum of the norm squareds of the z's has to be equal to 1. There are 3 of them, so that gives you S5. And then you're quotienting by the action of just quotienting by R, and that gives you finally, well, you're quotienting by the action of U1. That gives you CP2. So the proof of this proposition breaks down to, so first of all, why does N act freely on this level set? That is from standard material on symplectic quotients. A symplectic quotient, the group acts freely if and only if the stabilizer is finite. And you can check that in this situation, the stabilizer is finite. So finally, we define, so B is, our polyhedron B is in Rn star, and we will write its image under pi star that lives in Rd star. So I claim that I star composed with J inverse of 0 is equal to J inverse of B prime, which is equal to the set of points in Rd where I star composed with J of Z is equal to 0. So that means J of Rd is just the set of points x1 up to xd in Rd, so that the EI of, for all I in I up to 1 up to Rd, this just says that this is less than or equal to lambda sub j, lambda sub I. So I star of x is equal to 0 if and only if x is equal to pi star of y for y in Rn star. In other words, I star of j of z is equal to 0 if and only if j of z is equal to pi star of y for some y in Rn star. And we also are requiring that EI in a product with pi star of y is less than or equal to lambda sub I for I less than or equal to I from 1 to d. So that's equivalent to pi of EI is less than or equal to y for the same lambda sub I, the same I. So that says that u sub I of y is less than or equal to lambda sub I, which is the characterization of this polyhedron in terms of these intersecting half spaces. So this is if and only if y is in B, or pi star of y is in B prime. So that tells us that j of z is indeed equal to B prime. We also want to see that for z in CD, let's define I as a subset of the integers from 1 to d, so that z sub I is equal to 0 if and only if I is in capital I. So this is the 0 index set. So the stabilizer of z is T sub I, which is the set of points where the u sub i's are equal to the identity. So this is, oops. This is u1 to the power d minus the norm minus the dimension of I. That's the stabilizer. So that way you identify the faces. We also see that for any z in J inverse of delta prime, the stabilizer of z is transverse to n, which acts freely at z. This is because for faces f sub I of the polyhedron delta or of its image delta prime, these are determined by choosing a subset u sub I, comma y, which is equal to lambda sub I, for y in the dual of Rn, and E sub I is equal to, inner product of E sub I is equal to pi star of y. This is equal to lambda sub I. These conditions determine a torus T sub I in the bigger torus T sub D. Notice that the condition that I, this set of indexes, I is a subset of I prime. This is equivalent to the corresponding inclusion of faces f sub I prime is contained in f sub I. Notice also that the largest sets I corresponding to the vertices, f sub I equals a point. These have n elements because of the hypothesis that each vertex has n edges leaving it. Or equivalently, it is the intersection of n facets. If the vertex is the intersection of m facets, then each edge is the choice of one facet to omit. In other words, the number of edges is the number of facets. So for any I corresponding to a facet, it sits in several maximal I sub max with the dimension of I sub max is equal to h. This corresponds to the vertices in the face for which the face is equal to a point. So U sub I, where I is in I sub x, form a basis of the integer lattice in the Lie algebra of the maximal torus T. Notice that what I was denoting as the weight lattice, lambda sub W, is the dual lattice of the integer lattice, lambda sub I. The edges leaving the vertex P correspond to a basis of the weight lattice, which is dual to the basis U sub I, because T sub I is the set where Z sub j is equal to 1 if j is in the indexing set I. So this is the image under the exponential map of theta sub j of E sub j, where theta sub j is in the real numbers and E sub j is a basis for RD. So this is under the exponential map. You're taking the exponential of pi of T sub I gives rise to exponential of image of the theta sub j. Those are just real numbers, and the U sub j are our basis for the standard Euclidean basis for RD. So T sub I of Imx is isomorphic to T to the n. So since n is equal to the kernel of T to the d, the map from T to the d to T to the n, n intersect T sub I is the identity for any I corresponding to a face F sub I of the polyhedron B prime. This happens if and only if n acts freely on J inverse of F sub I. So n acts freely on J inverse of B prime. In other words, I star composed with J inverse of 0. I should ask, does anybody have any questions? Okay, by reduction in stages, which more or less means the standard result in symplectic geometry, it means that if you reduce by a subgroup, then the reduced space has an action of the quotient group on it. So this means t to the n, which is t to the d quotiented by n, acts on I star composed with J inverse of 0 quotiented by n in a Hamiltonian way. So the above results show that you have n goes to t to the d, goes to t to the n, goes to 0, and then dually Rn star goes to Rd star, goes to n star, goes to 0. So if Z is J inverse of B prime, which is I star composed with J inverse of 0, then J of Z is in the image of Rn star. And so phi sends M to Rn star, and Rn star gets mapped to Rd star, gives you phi of M is in the image of J. So I claim that for little m in phi inverse of F sub I, M being in phi inverse of M sub I, this is equivalent to the stabilizer of M being equal to T sub I, which is a subset of T to the n. So So phi of m is in the interior of B if and only if t to the m acts freely at m. Also, phi of m is in exactly one facet if and only if t to the n acts with one-dimensional stabilizer. Phi to the n is in the intersection of exactly two facets if and only if t to the n acts with two-dimensional stabilizer, and so on. Phi to the m is a vertex if and only if t to the n fixes m. Are there any questions? Okay. So finally, B is a subset of the dual of the Lie algebra of the maximal torus, which is Rn star. And we write the normals of the facets as U sub j. These are in the integer lattice of the Lie algebra of the maximal torus. This is true if and only if f sub I is the intersection of the plane, hyperplane, where the inner product of x with U sub I is equal to lambda sub I. For I in the index x set I, the U sub I generate the stabilizer at any point in phi inverse of f sub I. Finally, we see that if B is some point in the interior of a face f sub I, then the preimage of B under the moment map is isomorphic to t to the n quotiented by t sub I. In particular, the symplectic quotient of m at any point B is a point phi inverse of B quotiented by t to the n. So I will mention that a fan is the specification of a family of convex cones in Rn with origin 0, generated by elements U sub I in the integer lattice lambda sub I, and for which, first of all, every face of a cone is a cone. And secondly, if you have two cones, then their intersection is a face of both of them, so a face of C1 and also a face of C2. The data contained in a fan is dual to the data contained in the polytope B. One-dimensional cones C sub I correspond to rays R U sub I through the normals U sub I to the hyperplanes cutting out B. An indexing set I in the subsets from 1 to, in the integers from 1 to D, this has order R. Say it has an order R, then it determines a cone C sub I, we'll call U sub I1 up to U sub IR, of dimension R, which corresponds to the face F sub I, which was cut out by the intersection of the half spaces X equals inner product of U sub I with X being equal to lambda sub I for I in capital I. So such a face of codimension R. The origin 0, which is a zero-dimensional cone, corresponds to the face of dimension n. However, when you pass from the origin, from the polyhedron B to the fan sigma, you lose the information lambda sub I, specifying the distance of the hyperplanes in B from the origin. So fans classify toric manifolds up to diffeomorphism. The polyhedra instead classify toric manifolds up to symplectic diffeomorphism. For example, spheres S2 of different radius but the same center have the same fan. which is just a ray coming from the origin, but they have different Newton polyhedra, which are the intervals from -r to r, where r is the radius of the sphere. To construct a toric manifold starting from a fan, you note that for any indexing set of order r, the cone a cone C sub I may or may not be present in the fan, depending on whether or not the intersection of the hyperplanes is non-empty. We have, as previously, these exact sequences of vector spaces and also exact sequences of groups. These are real groups and their complexifications. So n sub c is c star to the d minus n. This is the complex Lie group whose Lie algebra is little n tensor product with the complex numbers. This is the complexification of n. So if I write E sub I as the set of z1 up to zd in c to the d, so that z sub j is equal to 0 for j not in the indexing set, then this has dimension absolute value of I. In particular, the E of the empty set is 0. So the toric manifold associated with the fan is m of sigma, which is equal to u sub sigma quotiented by n sub c, where u sub sigma is an open set in c to the d. This is what you get by taking c to the d and removing. These are points where c sub I is not in sigma. And then the ray E sub I corresponding to that. So an alternative definition is u sub sigma is equal to the union over all the indexing sets I for which c sub I is in sigma of the u sub I. And here u sub I is set of z in c to the d, for which z sub j is equal to 0 implies that j is in I. So this is c star to the, so this means I bar means the complement of I times c to the I. So the condition for a fan to correspond to a compact smooth toric variety is that you need the fan to be complete, so it covers the entire plane. You also need that c sub I is in sigma implies that E sub I intersect with the complexification of script n. That has to be empty. This is because each cone of sigma is generated by u sub I for I in the indexing set I. And this forms part of an integer basis of the integer lattice lambda sub I. All n-dimensional cones of sigma, which correspond to vertices of the Newton polyhedron, are generated by part of a z basis of lambda super I, the integer lattice. So, for example, suppose we have n equals 2, d equals 2, and we'll take the indexing set to be, so you could have empty set 1, 2, and 1, 2. So we have all possible indexing sets. So that means that u sub sigma is C2. You could also leave off the 1, 2. So that means that the condition that C super I bar is not in sigma is that I bar is equal to 1, 2. In other words, I is equal to the empty set. So that tells you that U sub sigma is equal to C2 minus 0. Finally, we can look at n equals 2, d equals 3. So we have the possibilities I equals empty set 1, 2, 3, and the sets with 2 elements, so 1, 2, 2, 3, and 1, 3. I'm not putting in 1, 2, 3. So if C sub I bar is not in sigma, then that implies I bar is equal to 1, 2, 3. That implies I is equal to the empty set, so E sub I is equal to 0. So that tells you U sub sigma is C3 minus the empty, minus 0. So if script n is equal to real numbers times 1, 1, 1 in R3, and n is equal to diagonal elements that are equal in U1. So that's a subset of diagonal subset of U1 3, U1 to the 3. Then we get U sub sigma is equal to C3 minus 0. So since script n is equal to R111 subset R3, and n is equal to this is U1 embedded diagonally in U1 to the 3. So we have NC is equal to C star embedded diagonally in C star to the 3. So we've recovered the more usual description of CP2, which is C star to the 3 minus, sorry, I think I mean just C to the 3 minus 0, quotiented by C star. Yeah, this should be C to the 3, not C star to the 3, sorry. So how do you recover a symplectic structure on a toric manifold specified via Fn? Suppose as before, we have C to the D mapping to R to the D under the map J, and there was also the map I star. So J was these quadratic maps. For any regular value, I'll call it psi in n star. I'll write psi is equal to I star of lambda 1 up to lambda d. We saw that a toric manifold was specified by I star composed with J inverse of psi quotiented by n. For any regular value psi, the manifolds M up to lambda 1 up to lambda d have the diffeomorphism type of a manifold M sub sigma, which is equal to U sub sigma quotiented by NC. So first of all, M sub sigma inherits an action of C star to the n, which is C star to the d quotiented by n sub c, which is the action of U1 to the n. And secondly, this action preserves the complex structure, but not the symplectic structure. The action of U1 to the n preserves both the complex structure and the symplectic structure. In other words, the Kähler structure. So let me finally remark that we have two constructions of M sub sigma. First of all, as a complex manifold, as the quotient of an open set in C to the D by the action of a complex group N sub C. And secondly, as a symplectic manifold, as a symplectic quotient of C to the D by the compact group N. The first construction is an example of a general geometric construction called geometric invariant theory. So what you do is delete unstable points from C to the D. These are points that would cause the quotient by N sub C to be non-Hausdorff. And so then you get C to the D minus a set with complex codimension greater than or equal to 2, all quotiented by N sub C. The general principle is that the symplectic quotient of a Kähler manifold by a compact group N is the same thing as the geometric invariant theory quotient by a complexified group N sub C. This you will find in the work of Attia and Bott and also Kirwan. So the main references that I've been using are Michel Audin, torus actions on symplectic manifolds. This is 2004. And also Victor Guillemin, moment maps and combinatorial invariance of Hamiltonian Tn manifolds. This is Birkhäuser, 1994. So I'll stop there.